Hello and good morning, night and afternoon, depending on your time zone or when you're viewing this. Last time we spoke about materials and their implications and how do you think about them, basically, in simple terms. Today we're going to talk about loads and loading paths. So let's hook the iPad and hopefully you're going to enjoy the ride today. That's the plan, I suppose. Okay, just 2 seconds. Yep. So, introduction. By the end of the session, we'll be able to understand the following. Loads, their types and classifications. Let's come closer. Loading paths, examples, and how to tackle them, and the basic principles of global stability. So all these three things makes you understand the structure as a whole, to feel it, to sense it, to know what's happening when loads tackle the building. So we're going to talk about loads. Loads are the actions that the structure and its elements must withstand in order to achieve its intended use. يعني المبنى يكون عليه مجموعة من الأحمال أو مجموعة من الأوزان لازم يشيلها ولازم إنه يشيلها عشان يكون static. فضروري نعرف إحنا أنواع اللودز. So loads acting on the structure include the following. First, dead loads. أحمال الميتة يسمونها. Dead loads are permanent or stationary gravity loads, which are transferred to the structure throughout its lifespan, and it includes self-weight of all the structural elements and non-structural elements. طوفة مطوفة والسوالف. Non-structural elements, الطوفة مو structural element على فكرة يعني. طوفة or the wall does not contribute to the strength of the building as a whole or stiffness. There is a little stiffness component, but let's ignore it for now. So the loads that stay throughout the whole of life's building time is basically called, or are basically called, dead loads. So the calculation of dead loads of each element is carried out by multiplying the volume of each section with the unit weight of the material. Unit weight is basically gamma, which is rho times g. And the volume is the volume, which is a dimensional component. You could find it out from mathematics, basically. So that's how you get the weight, basically. Follows are some of the popular unit weights of structural and non-structural members. So these are like things that are useful when you have an aluminum corrugulated or maybe asphalt or carpet or whatever. They give you it by an area load. Why an area load? Because when you're using software to design, you actually need to understand that you have two ways of, or three ways of dealing with loads, either as a point load, which is an application of a point, and you have to think about it as an area load, an application of an area, which means that it's kilonewton per meter squared. And you have another way of thinking about it when you have like a line load, which is طوفة مثلا, you have to use it as kilonewton per meter. These tables give you it already transferred to per unit area. So it's very useful. So you just like plug these numbers inside your program and you're gonna have results. Yeah. Let's go somewhere else. These are materials as well. Typical self-weight of concrete floors per unit area. نفس الشيء عندنا هني. Typical loads for sheet materials. Sheet materials include عازل معازل والأشياء هذه. ما تشوفون أشياء مهمة مثل screed, plywood if you're dealing with temporary works. Plywood الخشب اللي يستعملونه في البنيان عادة إذا ما قاعد تستعمل فريم حديد. Anyways, these are per unit area. بعد خلينا نشوف هذول. These are typical loads for walls and cladding per unit area. Walls and cladding أشياء اللي تتركب على واجهة المبنى. The facade basically of the building. Cavity wall, lightweight cladding, insulation, the walls outside, timber cladding, if you have precast concrete cladding, brickwork, all that jazz. So now, note that these are just to guide you to make sure that you have a good estimate of your dead loads and serves as a guideline. Codes and regulations in every country has its own documentation, yet بالكويت احنا عندنا this is accurate enough. Just use these عادي, no problem. Imposed live load. This is the second type of loading that we have. These loads are non-permanent loads that depend on the functionality of the structure, like the type of partition and furniture. هذا الاشياء تتغير في المبنى. الأثاث مثلا أنا غيرت مكان السرير من المكان الفلاني للمكان الثاني. It should be included in live load. طاولات مثلا, people, the weight of people. If you have a very packed classroom, is considered live load. What else? Anything else that fits that criteria. It's basically a concept, an idea. Live loads is an idea. You won't make a fatal mistake if you mistake dead load for live load with some certain stuff, but you make sure that you are consistent and you basically try to get it accurately, because the factors of safety for dead load and live load in all codes differ, because dead load is considered more accurate because it's mathematically derived, while live loads are not considered mathematically derived, لأن عدد الناس الموجودين in a building changes with time. But the dependency of the data statistically is less. عشان كذي الفactor of safety مال اللودز مال live loads يكون أعلى من الفactor of safety of dead loads. These are usually made as an educated guess on a structure or by using design codes. Figure 2 shows the Eurocode values for live load. These are basically the same concept, yeah? Kilonewton per meter squared, or as a concentrated load as kilonewton if you need it as a point. This is as an area that you want to plug it in a software on a slab. Loads on a slab area. Hello? Actually, let's write this down. So loads on columns are point loads. هذا column, for example, is a top view. احنا نقول ان the point of application is the middle point. Either loads on beams are line loads, يعني per meter. يكون بهالطريقة. إذا هذا البيم نحط خط هني يسمونه the structural application line, يكون اللود بهالطريقة على the point of application line. Loads on slabs as a family are area loads اللي هو per meter squared اللي هم هذول. هذا concentrated for column, slab. طبعا we could basically multiply by the length and we get for beam as well. يعني في طرق وايد. إذا هذا السلاب كل مكان basically has the area load. Note, a common mistake sometimes is changing the purpose of the structure without checking if the values used for the design assumptions can withstand the new intended use, which maybe does not lead to a complete collapse, but they affect the serviceability requirements, اللي هم من serviceability requirements, floor vibrations and deflection. هيغير the floor vibration values and the deflection value of the structure, which are correlated in a sense. شنو المشكلة? We have a warehouse and we changed the warehouse اللي هو المخزن, مو warehouse, let's say عندك غرفة تخزين في البيت, like a place where a storage area in the house. Hello? Or you needed a storage area in the house, so you turned the bedroom into a storage area in the house. يعني شلت الغرفة هذه, شلت الفانكشن مالها من غرفة نوم إلى غرفة تخزين. يفرق. The live load assumption that you use for storage areas is different than, or more than even, the values you use for a bedroom. So what happens? You start, even though your building is not over-designed in a sense, which most buildings are, then you're going to have these problems, basically. So you could go through these after I stop. If you need these lectures, just email me. I'll send them to you. Completely free. Wind loads. Now we're going to talk about the third type of loading, which is very important. Wind loads. Now we're entering the time domain into the equation. Time dependent. Wind is time dependent. So wind loads are loads of cyclic nature. Cyclic means what? Time dependent. 1 cycle, 2 cycle, 3 cycles, etc. That alternate between suction and compression. يا بالضغط or بالسحب. This topic is complicated and always needs a good explanation. Okay, let's talk about some cases. خلينا نشوف الكيس هذا اللي على اليسار. We have wind loads getting portal frame. Frame عادي مظلة basically. What happens is we have here uplift pressure and here we have internal pressure building up. Okay, this side is called windward and that side is called leeward. Good terminology to keep into your head, because when you talk to other engineers, you're going to talk about the windward direction and you're going to talk about the leeward direction. Now let's talk about some phenomena. Yeah, just a point, yeah, that this is not important for short buildings. Anything 3 floors down, you're not considering wind as much unless it's يعني شيء unconventional and long span and has a hole بالواجهة ممكن you consider wind load. But for skyscrapers, for high buildings, high-rise buildings, no, it's very important. It's actually detrimental. It's a design parameter. It's a main design parameter. So now let's consider this building, basically. What happens when wind hits the building? This is the wind load in red, hitting a surface of the building, and there are 2 corners. What happens is these are going to hit the building and react on the surface of the building and get distributed throughout the building. But we have winds that come around the building through this corner and through that corner and go back to the building and cause what we call vortices. So these are vortices. These vortices are very important when designing skyscrapers. You have to solve that problem because remember, you're pushing from this way. Now with the wind load, if the wind comes back again and starts to push the building the other way, we're going to have a cycle now. And that's a problem. We're going to talk about, like, when we talk about some dynamics lately, we're going to understand what happens here. So it's same here. Wind hits this side, wind hits that side. إذا في opening مني طبعا, that's what the opening مني مثلا. These surfaces are going to be affected. Here, if it's a closed building, all these surfaces are going to be affected, etc., etc., and the surface as well, to be fair. So now we're going to talk about another type of loading. It's called earthquake loads. Again, cyclic in nature and time dependent. During an earthquake, the damage that occurs in the structure depends on many factors like the intensity, duration, the frequency of the ground motion, soil structure interaction, and the dynamic characteristics of the building, such as natural frequency and critical damping ratio. Complicated, right? So all these topics we're going to unpack in its own sense when we're talking about earthquakes, maybe lecture 13, I believe. We're going to talk about them separately, but take it as in face value, basically, that we're going to have a lot of parameters, just like an introduction. This is an introduction to loads. In an earthquake, that's the story now. We're going to tell a story. In an earthquake, the ground starts to shake, and that would create inertial forces that are caused by the weight of the building. Inertial forces, هي weights تعتمد على the mass of the structure. Yeah, and when you have higher mass in a structure, then you have more inertial forces. And that's a problem with earthquakes, because usually they would tell you to increase the section when you're failing a criteria. Like if you're failing an earthquake criteria, increasing the section is not an option. Because when you increase the section, what happens is you have more load now, more inertial forces. So more earthquake load, which basically means that you're going to collapse. easier. Anyways, earthquake loads are often expressed in terms of G, 1G, 1.5G, etc., a function of the Earth's gravity. The problem with an earthquake is you have this type of movement now. So this pushes the building, and at T equals 2, for example. It's like we said, T is time dependent, and the load mali is time dependent. So T from 2 to 10 means that in these 8 seconds, I have movement. During that 8 seconds, this pushes the building and then pushes back. This pushes the building again, pushes back. So that's basically, it's a lateral load that is time independent and reversible. Again, when we're explaining the earthquake loads expansively in lecture 13, we're gonna see some diagrams and see some movements and videos, and it's gonna be a very good lecture, lecture 13. I'm looking forward to it from now on, it's lecture 2. Yeah, so we have the gravity and inertial forces here, bad. Yani, when that happens, that does not mean that the weight of the building is not there. The weight of the building is still there. It's redirected, but not all of it. Some of it's still pushing now. Some of it is pushing laterally now, creating inertial forces. So now, and even wind sometimes would be present as well. Here I'm saying that we have the inertial and wind and dead load as well. So you have to look at all these cases. Computer programs do that very well, combining equations. That's what they do. They just combine equations, solve for you. They just solve for you. You're the brain and they're the muscle at that point. So it's a 3D load. We idealize it. ساعات we نحط له idealization, like, oh, it's acting that way, it's acting, but in nature, it's a 3-dimensional force. Yeah. So now we're going to talk about the second topic of this lecture, which is loading paths. We have a case study here. Concrete frame building subject to live and dead load. Open exercise. Usually this will become very interactive, but I'm going to ask all the questions and try to answer as much as possible. This is very uniform. We have a uniform load acting here. What happens is half of it will go here, assuming centrality in the guy acting بالنص, and the half of it will go the other side. So, and they travel through the columns floor per floor per floor until it reaches the foundation. And this building, the foundation type, for geotechnical freaks, foundation type is a basement foundation. Not very common. Actually, it is very common. بس يعني مو بكل مكان. It is, no, I take it back, very common. Basement foundation. And you have the soil reaction. So the free body diagram now consists of load, path, and then soil reaction. Soil reaction is never a point of application unless you're idealizing. Again, we use a lot of idealizing. This is a cute building because هذا بير أصلاً صير basically. This is basically services room. Can't spell today. Services room. Very cute. And you find it in every building. طالعون البيوت الحين in Kuwait, all buildings kind of have this room up top for an elevator shaft. This is a simple case, like we're going to build up. Case study. Steel building subject to wind plus dead plus live load. What are the loads acting on the structure? On the loads acting on the structure, the self-weight of the truss, members, roof tiles or purlins. Roof tiles الأشياء تنحط على الروف ككسوة is called a purlin. Given the wind direction, how will the load path be? If the wind direction is here, basically, wind at somewhere 0 degrees, what happens is you're going to have this reaction, basically. اللي هو بالأزرق in blue. While in red is basically the dead load plus live load. Okay? Direction. These purlins, وهم في wind load bad and wind load as well. Yes. Okay, and wind load as well. Sorry, my references. So yeah, why know this? ليش مهم? Wind could strike from this side as well, and the diagram will just like change, but it's the same thing, yeah? This travels from the outward kiswa and then goes to the beam and goes up as well, and the wind is hitting this way as well. So through the bracing and into the structure. You have to think of it conceptually. How is the load moving? It goes here, then goes there, it goes here. You have to imagine that in your head. Why know this? So when you get values from analysis, you know if they make sense or not. When you analyze the structure through a computer program or through anything, what happens is you get results. And if the results basically are way off from whatever you're expecting, you will basically calm down and go like, okay, did I make a mistake or did the computer make a mistake? And you start to analyze the problem. You go like, whoops, I made a mistake. Or maybe, wow, the computer made a mistake because you made a mistake in the beginning, you know, maybe with a node, maybe a connection, something. So now, again, this is the concept that, you know, some professors used to teach us, which is rubbish data in through a software would give you rubbish data out as a design. So if you have shit data going in the system, then shit data would come out of the design as a design, basically. Case study number 3. Case study number 3. Open-ended question. Usually this is very interactive. So a water tank. I'm not going to say Italy because Italy is an earthquake zone. I wanted to make this an earthquake exercise, but yeah, bias, I guess, just like earthquake design. So this is bias due to, oh, what's happened? What is this? Oh, sorry. Due to bias. How will the loads, what are the loads that will be into question? And how do we calculate them and load paths from top to the foundation? Okay. So now, configure. So basically we have, I've done this already. So first we have a load on top of the whole strip. Yeah, should have drawn this before. Very therapeutic, right? Yeah. This is Q as load, wind plus, rain plus snow. Okay? Usually put them, in the program you put them separately, but for the sake of argument, I'm just gonna say this. Wind is something and snow is something else. You might have rain, but not snow. Then you have wind load, basically. Symmetrical structure, yeah? So when like from this side or that side, it's the same thing. It's a symmetrical structure. It's a circle, basically. And we have dead load mini. GK is dead load notation. This is an oil tank. So we have the Q oil. And we have Q oil. What do we have more? So we have as well the dead load of this slab, the dead load of this slab, GK. And we have other things as well. Okay, we have other things as well. So let's actually draw this. Okay, let's actually draw this. So I'm not the world's best sketcher, but I try my best, I swear. Wasn't gifted in that department. So just a side note before I go into this, why do we have this longer than that? Because wind intensity increases with height. This is a lid. So the lid has a weight. And the weight of the lid, which is all this area, will boil down to go into these two sides. Put them in another color. These are basically structural elements now. Why? They're walls. The lid is something to be carried. What's carrying it? These walls. What's carrying the walls? The slab foundation. What's carrying the slab foundation? For example, piles. Ground level piles, for example. Or maybe just a slab on the ground, depends on the weight. So now, شنو عندنا acting? What's the free body diagram concerning this now? We have قلنا the weight of the lid will be divided هني, half of it will go here and half of it will go here. This is Q lid over 2, Q lid over 2. Am I even spelling lid right? Anyways, you get the gist. We have Q oil, and we have other types of pressures, by the way. We have this pressure now called hoop pressure. Creating tension. Creating the tension, basically. This is also called circumference. Now that I'm reminded, circumference as well. Sorry, where is it? Hoop or circumference load acting on the tank. Funny story that me and my colleagues during the master's course, we designed a similar structure to this, yeah? Like I borrowed this from that, and we designed for everything under the sun, yet we forgot to include the hoop pressure into consideration. And we all got we all got A's basically. So I'm not sure that even the professor didn't even maybe know that hoop pressure exists. I found out this like really late in the project, and I was like, I'm gonna include it. Anyways, enough stories. So these are basically the reaction forces of the piles. Soil reaction forces. And we have the self-weight, yeah? Self-weight of the whole thing. Okay, we have a problem here. When we're calculating loads عادة شنو قلنا احنا في البداية? Volume, right? And areas. Now we have a circular area, right? We have a circular area. And that circular area has a parameter because this is empty from the inside and we're going to fill it with water. So we're always going to use something we call the parameter in the calculation. So the parameter multiplied by the height here would equal my volume, usually. When we're calculating loads, we have to multiply by a volume. This is the volume that we're talking about. It's the parameter multiplied by the height. Okay. When we want area loads, sorry, volume, we need to add thickness as well, multiplied by thickness. If we're calculating the self-weight, then the thickness comes into play. But if we're calculating only the area that's going to be around this surface, for example, the hoop stress, yeah? The hoop stress, just like that, basically. The hoop stress, we're going to need the parameter multiplied by, اللي هو المحيط, multiplied by the height per unit area. Very cool example, to be honest. Like, let's recap, yeah? Water tank, oil tank, whatever. So we have a lid, and we have walls supporting, we have the slab supporting, and we have the piles supporting. And all of that is facilitated to carry the oil inside the lid and the structure itself. Cool. This is a free body diagram. Some people will maybe think there are more stuff like we said, wind fee, right? So we combine these two pictures, yeah? We combine these two pictures and we get the bigger picture. This is the free body diagram. We have wind load as well acting, and we have snow acting, and rain, depends on the situation. Maybe we have some underground water bad. Since this is the ground level, we have underground water acting on the piles, causing overturning. There's a lot of things we're going to talk about. Okay, now the principles of global stability. Now we're thinking of the building as a rigid thing, and we're trying to find out what happens to that rigid thing when we hit it with multiple things. This is an important check that each building in its conceptual stage must undertake in order to identify what loads are going to cause instability and what mechanisms that resist that. So any load that would cause instability must have a mitigation. That mitigation mechanism is a resistance. It's a safety for the building. So when you're designing something crazy, yeah, with curves and cantilevers, and you have to always account for the global stability. هل المبنى مالي بشكله geometrically ثابت? Some people would tell by the eye, some people would have to break it down into summation of forces and all of that. Yeah, something has to be there to mitigate. If there's nothing mitigating, then collapse. We have to have static system here, not a continuous system, a static system. We're talking about discrete, static discrete system. Summation of forces should be equal to 0, and summation of moments should be equal to 0. So an open-ended question I usually ask is, when is stability achieved? Some movement, think about it. Think about it yourself, and maybe don't ask or whatever. So let's look at this stable, rigid building. We have wind load hitting it. Yeah, we have wind load hitting it, and that's the resultant of all the dead load and the live load and the wind load. And that's the resultant. There is an angle here. So what happens to the building as a whole when you hit it with wind load? Only beams and columns now. We're talking about the building as a whole, the whole entity. Some piles will be basically placed under compression or ضغط, and the other half of the building will be placed under tension. Same with the piles here, compression, tension. This is compression, this is tension. This is important because you have to design the building to withstand all of these. So you hit it with the wind this way, then you hit it with the wind that way. You hit the wind windward direction in the paper, from the back of the paper. And all of these things, all of these piles should be able to withstand tension and compression. So now when you're thinking, okay, this will cause compression. What's the mitigating or the stability providing elements? Oh, these that are placed in tension. They'll maintain equilibrium. Same when you reverse. So when you're thinking, okay, there's a seat belt for compression, and that's the tension here. Yep, I think that makes sense. Now we're going to talk about some popular modes of failure of buildings. Modes of failure of buildings, not single elements, because we're going to talk about every single element later and explain the modes of failure of each single element. So after you take all of these into account, or maybe before you even take all of these into account, your conceptual design stage is in play, and you want to know what are the modes, the popular modes of failure that you should be basically remembering when you're designing a building. Popular modes of failure include sliding, overturning, twisting, and raking. Overturning is this one, the basically tips. Raking, it moves in that sense. Every corner moves independently. That's raking, back and forth, basically. And you have sliding when you have like a flood, a water tank that hits a flood from the outside would be slid to the side. It's a failure through sliding. And we have twisting. Twisting is usually earthquakes related. You have them building twisting with creating torque on the structure. And believe me, structural members, especially concrete members, hate torque. So we have another case study here, revising wind load and introducing beams and columns. Okay, introducing diaphragm action. Bad. So basically, we have a load mini, like we see, that's how it goes. Yeah, we've done this with the frame already. Introducing beams and columns. So these are columns, yeah. These are columns. These are beams. We have something called here wind posts. Wind posts are basically considered beam columns. We're going to talk about them when we're talking about beams and columns more. Introducing diaphragm action. Yeah, the slab thickness is very thin compared to its width. Yeah, because what's a slab? This, right? That's a slab. So its thickness is very width is very small, because it's very thin compared to its width. So its moment of inertia is very large in its own plane. What I mean is this plane. A moment of inertia basically is a function of how the body deforms under load. So if it's very large, it doesn't deform much. Yeah, so they have enough shear between them and the concrete frame because they're not deforming. They sit on top of it basically to transfer the load to the main structural elements and then to the foundations. Okay, we're going to explain this better. I've written it down. So yeah, I'll do this here even. So if wind hits mini, see, it's not going to deform this surface much. So what happens is it transfers, yeah, very large, as we said. This is the plane, this is H, the thickness, B, width. We have diaphragm action, which means that the slab, اللي هو الخط الأسود اللي فوق, sitting on the frame, would transfer the load because it's not deforming, because of its large inertia, to the frame itself. Simple concept. It's not very simple, but it's like graspable. That's a word. Stability. Note that stability systems will further be inspected in earthquake. All right. So let's see. Here I explain it even better. Yeah. So we have this node and this node. Yeah. So slab sits on top of a frame. We're explaining diaphragm action again for the third time. Sorry. So we have wind hitting the building and we have self-weight. Bad. This red moment diagram, our deflected shape, is due to gravity, and that's how it transfers the load. So gravity loads are transferred by bending. The beam bends and it transfers the load to the columns here. But in case of diaphragm action, yeah, what happens is you have that wind load اللي I just put it مني عشان كبره يعني. So we have this pole bending that way, yeah. But this thing اللي هو فوق is not bending. It's basically transferring through shear. Like I said, very difficult to bend, so it transfers the load through shear. That's what's called by diaphragm action. That's why it's very important. If you're designing concrete buildings for earthquake or wind, concrete is very much preferred because basically, okay, though it's heavy, you could make it a bit light. It would actually have floor diaphragm action, restraining columns back and beams. We're going to talk about restraining conditions later, but for what it's worth, diaphragm action transfers the load through shear, lateral loads through shear to the structural members, like we see here, basically, and here. That's basically here. Now, case study, how would you go about designing this building? So basically, I'm just like throwing you a curved ball here, you know, just play with it. It's basically a maritime tower. We had this project like for a full year to design, and I could share a document with you if you want to see how I tackled the problem at least. And a couple of friends had different ideas, and we all got good grades from this. So I'm really happy about that design. You can just email me or WhatsApp me ideas. Basically, what are your ideas in designing this? So you could apply all the concepts that you studied throughout this lecture, the global stability, and all of that, just and send me. I'm a really curious guy, and I will not say no. I'll just look at your stuff. Don't worry. I'm very curious how people think, and not only in the engineering sense, in general. So I like to see how different brains interact with the same problem. So yeah, that's basically it. We have some references here. Yeah, and hopefully this lecture was beneficial for you, and I'll see you in the next one. We're going to talk about something even more important and intriguing, which is basically how to turn architectural drawings into structural drawings. This is basically the best lecture, I think, in terms of maybe interesting things are in the earthquake, but practical stuff that you basically have your brain working when you're looking at buildings in the street. After lecture 3, I will basically bestow upon you a plague that you'll be staring at every ceiling that's exposed, looking for like the structural system. That's basically will be ingrained in your head. You'll never forget that. You're going to remember, oh, this, the other thing. And thank you very much for, if you stayed this long, I mean, congratulations. You take care, and I'll see you next time.